In this video, I'm going to show you 3 different ways to solve this definite integral. So this is asking us for the area from x equals 0 to 3 between the function y equals 2x minus 2 and the x-axis. And so the first way to solve this is by setting up a Riemann sum. Remember, the Riemann sum is just taking the limit as your number of rectangles filling this area goes to infinity, n goes off to infinity, my number of rectangles goes to infinity, of my width, where it's my total width, so 3 minus 0, b minus a, all over n times the sum of my function, where I began at the left-hand side, a, and I had copies of the width, 3 minus 0 over n. I had I copies, where I is an index going from 1 to n. That's just counting off the n rectangles, giving me the height of each of those rectangles, and it's the sum of each of those heights times your width of the rectangles. That's our formula for the Riemann sum. So we can go ahead and solve this now. This is just the limit as n goes to infinity of 3 over n times the sum, where your index goes from 1 to n, of this is just 3 over ni, that just simplifies to 3 over ni, and you plug it into your function, where here's my function right here, so it's 2 times x, so I'm plugging in for my x, 3 over ni minus 2. So that's what I need to calculate. Now we simplify, so we can distribute the sum to try and get the I by itself. So simplifying, we get the limit as n goes to infinity of 3 over n, your width, times, now distributing the sum, 2 times 3 is 6, so 6 over n times the sum of my I minus just the sum of 2, where I equals from 1 to n. Okay. Here, we're going to think back and remember, what is the sum of I from I equals 1 to n? Well, that's just 1 plus 2 plus 3 plus 4 all the way up to n. And that came out to be, you recall, n times n plus 1 all over 2. Likewise, you can think about, well, what is the sum of 2 from I equals 1 to n? Let's say it's just 2 plus 2 plus 2, n times from 1 to n. So 2 plus 2 plus 2, n times, that's just going to be 2n. So this will now simplify to, let's see, we have a 3n times 6 over n, so we have an 18 over n squared times this first piece minus 3 over n times 2 over n, and then taking the limit as n goes to infinity. So simplifying a little bit further, let's see where we land. We get the limit as n goes to infinity of 18 times n plus 1. That's 18n squared plus 18n all over 2n squared minus 6, because that n and that n just cancel, minus 6. And as I take the limit as n goes to infinity, that's just 18 over 2, so that becomes 9. 9 minus 6 is 3. So I get, using a Riemann sum, this is 3. Okay, you can do that. You can do Riemann sums. But it turns out in this problem, there was an easier way. We didn't have to do all the work we just did. So here's an alternative way we could have seen this. Instead of doing this Riemann sum, we could begin by just looking at a picture. And so let's think about what this graph of 2x minus 2 looks like. Well, it's 2x minus 2, so it begins here at negative 2. And it has a slope of 2, so it's going to go up 2 over 1, and then up 2 over 1, and up 2 over 1, which now gives me, okay, missed the point, but gives me something like this. That's what the graph of this looks like. It's just a line. It's just a line. And so now let's take a moment to think, what is this area from 0 to 3 of 2x minus 2? Well, here we need to remember the definite integral represents the signed area. That is, over here, from x equals 0 up until x equals 1, all of the corresponding area is negative area. This is negative area. And then, when you get to the right, from x equals 1 up until x equals 3, the area between the x-axis and the graph is positive area. So you can say this area from 0 to 3 is just the area from 0 to 1 plus the area from 1 to 3, where this area from 0 to 1 is this little negative area, this negative area here, whereas the area from 1 to 3 is this positive area, the slice here, which is positive area. And these are just triangles. So we can actually find these areas using good old-fashioned geometry, right? Like, how big is this triangle? In this case, from 0 to 1, from x equals 0 to 1, the width would be width 1, because you're just going from 0 to 1. So the width is 1. And what is the height? Well, you're going down 2. So I'm going to put a negative 2. It reminds me that I'm going down, and that's how I'm going to get a negative area for this guy. And so this triangle ends up having area negative 1. 1/2 base times height, negative 1. It's negative because it's below the x-axis. You went down for your height, negative 2 for the height. So the area is negative 1. Whereas the second guy, the second triangle, has width 2. From 1 to 3 is width 2. And has height from 0 up until here, which is height 4. This is height 4 here. Because when I plug in 3, I'm at height 4. Plug in 3, you're at 6 minus 2 is 4. And now you find the area. My area for the second guy is 1/2 base times width. It's a triangle, so it's half the rectangle. So half of 8 is 4. And so then I conclude that my area, this definite integral, is just negative 1 plus 4, which is 3. The same answer I got before, but just doing a little bit of geometry, not needing to do a Riemann sum. Now, what helped us here is that these were triangles. If this had been a parabola in x squared, for example, I wouldn't know what the area is. I would need to use the Riemann sum method, at least for now. But when it is a familiar geometric shape, then you can just find the area of that shape. But I promised you 3 ways to solve this, and we've only seen 2. The third way to solve this definite integral is to use our properties of definite integrals. And the properties I have in mind is the fact that when I have a definite integral of f of x plus g of x or f of x minus g of x, I can break it up as 2 separate definite integrals. The definite integral of 2x minus the definite integral of 2. But more than that, so I can break this up as 2x minus 2. But more than that, this 2 here I can also pull out. When there's a constant times something, I can pull it out. So I end up with, it's just 2 times the definite integral of just x minus the definite integral of just 2. Now, let's think about these functions. This function x and this function 2 are even easier functions than before. So this is going to be an even easier geometry than before. For this first piece, what does the function x look like? This function x, if we're to draw its graph up to 3, from 0 to 3, it would be just the line y equals x, which again, this area is just the area of this triangle. A triangle of base 3, height 3. So this guy has area 3 times 3, which is 9 divided by 2. But then there's this times 2 out front, so I need to times the whole thing by 2. So the area corresponding to the line y equals x was just 3 times 3 divided by 2, because it's a triangle, 9 over 2. And then times the whole thing by the 2 up front. Minus, for the second piece, I want to think about what would the area under the line y equals 2 looks like. So this is some line at height 2. Well now, when I find the area from 0 to 3, this area here is just the area of a rectangle with base 3 and height 2. So that rectangle has area 6. But then you end up with the area of this definite integral is just 9 minus 6, which is 3. Okay, so this method was a little bit like the method before, but before we drew the geometry, we first simplified by breaking up this equation into getting some simpler graphs. Instead of the graph of y equals 2x minus 2, it's just the graph of y equals x and the graph of y equals 2, and then we piece them together using our properties of definite integrals. So that's 3 different ways that you can solve a definite integral when you know how to find the area when it's a simple shape like a line.